We've covered everything. We made our way around. Hydrates, hydrants, acetals, Wolff-Kishner. Wittig reaction. Next week our lab is, we're doing the Wittig reaction in lab. Okay? This is a group lab. We have a choice of starting materials. If you want to form a group and choose your starting material ahead of time, that's fine. Groups of 3 or 4. If you want to choose your starting material, then you can let me know. And you can have priority on your starting material. That way you can look up your melting point before lab if you'd like. We will cover the Wittig reaction in the lab lecture, so before we have lab we'll meet down here. Although on Tuesday we'll have to meet over there in that far room, over in the other building, like we did at the beginning of the semester. So we'll cover a Wittig reaction before lab next week. Let's finish up the handout. We got, I think we have to synthesize some meth. Is that where we left off at? Reductive amination? Yeah. Yes. Questions about lab report? Maybe lab report due when you come to lab next week. Question?
When we label like the IRs and NMRs and stuff, do you want it to be labeled in pen or can we do it in pencil?
I think American pencil would be okay as long as it's, of course, legible. And see why pencil is not okay. Okay, we're here, guys. Let's get started. Here's some compounds of interest, potentially. The structure here, phenylpropanolamine, PPA. You find PPA in some diet pills and over-the-counter, like no-dose pills, keep you awake type of thing. PPA, yeah. If you take the OH off of PPA, this would be the OH off. Really, you just remove the oxygen because you got the H still there. That's amphetamine. Okay, so which we call speed. So this is close to speed. You know, it'll make you get up and exercise and lose weight and stay awake, but not as bad as amphetamine would. Over here, if you put a methyl on PPA, you have Sudafed. That's a decongestant. So with the N-methyl. But you take the OH off of Sudafed, and now you're like amphetamine, but with the methyl on, it's called what? Methamphetamine. Okay? Well, these two here are sort of drugs. You know, this one's kind of illicit. This one's given to kids to keep them awake. It's called Adderall. Those up top are sold at the drugstore. Although you can't buy Sudafed anymore over the counter. You have to show your ID to buy it, or something. You used to could go in and buy like a case. You know, but why would people go buy a case? Because they would convert Sudafed to methamphetamine because you can remove that oxygen. There's some garage chemistry where you can do that if you know enough. Okay, so people were making meth from Sudafed, so now the Sudafed's restricted. Okay, so that'd be the meth lab approach. What are other approaches? Could you make this by a reductive amination? Well, actually, yes, there's 2 approaches to make meth by reductive amination. Anybody have starting materials? Uh-huh. Can I show this on the overhead? Yeah. Start with this ketone called reductive amination. Is going to have an aldehyde ketone and an amine. They come together to make imine, and then you reduce that down. So you came with this ketone, methylamine, to make this imine. In brackets here because it's not isolated. Or you could isolate it. You don't have to. Use sodium cyanoborhydride or H2 plain carbon to reduce the double bond. You lost your methyl. Right? Yeah? Should be methyl here, right? Right?
Yeah.
Okay. Hopefully that was just an oversight.
Probably is.
Yeah? Yeah, so you start with this ketone and methylamine. Yeah. That's actually the way they were doing it on the Breaking Bad show. Because they quickly got away from the meth lab approach and they went to a more sophisticated approach. And this has got a name, I can't recall what the name is or the 3 letters or something, but they said this. But then when I told them, they broke into a warehouse and y'all remember that show?
Yes.
I'm not getting too old, are we? They were trying to steal methylamine. And they had a big barrel of it, and I think it said methylamine on it, and then the police came or something. Or, I don't know, I don't remember. But they were trying to steal methylamine because they were, I don't know how they were reducing the imine. There are other ways to reduce imine. I don't know if they had a supplier of sodium cyanoborhydride or what. What was the other method? Yes. Basically, you can make this bond here, or you can make that bond there. Which amine, which carbonyl? This method made the bond on the left, correct? Well, how can we make the bond on the right? You're going to have your amine, the NH2, and then the methyl could come from the 1-carbon aldehyde. That's formaldehyde. This would give, not that. No, hold on.
The bond should be on the other side.
You got the double bond on the wrong side.
My bad, yeah, it's the other side.
You got the double bond on the wrong side. Aldehyde, amine. We get boom, nitrogen. Double bond to carbon. You can draw the carbon in if you want, 2 H's. You can draw everything in if you want. What happened? The nitrogen replaced the oxygen of formaldehyde. Then when you reduce it, well, this just becomes NH and CH. And so that's going to give that. NH and another CH. When you put another H on that, that carbon becomes a methyl, right? So this is the simplest type of carbonyl compound you can have. That's called formaldehyde. So that'll be formaldehyde or methylamine and this ketone. This is a reductive amination. Two different ways to make methamphetamine.
So in general, was the science on that show, the chemistry was pretty on point?
Yeah, I read that they actually had like advisors. There was some chemist at like University of Oklahoma that was one of the advisors or something. Somewhere in the Midwest or something.
What kind of a yield do you get on that reaction?
And what's your profit?
Yeah.
How
much Sudafed do you
I mean, you know.
It's online. It's online.
Purity, yield. I mean, you guys, you know, you do reaction labs and sometimes you get good yields and sometimes not. Okay. I think we've already looked at these two things. We ended last time with the metabolism of amines, where you can go backwards to the amine, and then that can be hydrolyzed, and that's how you can end up with a carbonyl compound as a metabolite. That was shown on that page. The last is the VIDIG. Like I said, we're going to do VIDIG in lab lecture. Please be prepared for that, though, because we'll do it. Try to do it quickly. VIDIG. Looks like Wittig, but the Germans pronounce it VIDIG. Anything in the white handout? Applications. There's a synthesis there that includes a reductive amination, then Davidic. I think we'll look at this more down the road. Time to move to the blue handout. We'll have a quiz on Friday over everything we've covered up to now. It is. Okay, new handout. Okay with the light off? Might be all right. Yeah. Okay. Alpha carbonyl chemistry, also known as Enol Enolate chemistry. Still aldehydes, ketones. Ketones here in these examples. Instead of looking at the carbonyl, we're going to move next door. So-called alpha carbon. Okay? Turns out that these hydrogens on the alpha carbon, alpha to the carbonyl, have some acidity. These are all ketones, pKa of approximately 20. Now that's not highly acidic. Alcohol is about 16. Phenol is 10, carboxylic acid is 4. But it's acidic enough that we can do chemistry with. We'll also do alpha to esters and alpha to nitriles. These are not quite as acidic. The ester is not quite as acidic because you've got the donating oxygen. First off, why are these acidic? Why do these have some acidity?
The resonance by the carbonyl.
Well, we want to consider where we're going. If we make the anion, and there's 2 hydrogens still remaining, if we make the anion after that acted as an acid, why does this have any stability? Well, yes, it's resonance stabilized with the carbonyl. And we're actually putting the charge onto an oxygen. Good stabilization. Resonance onto oxygen. Stabilization of the anion makes these hydrogens a touch acidic. Acidic enough that we can do chemistry with them. Why is the ester less acidic? Because if we're asking these electrons to move into the carbonyl like that, what is this oxygen doing?
Trying to do those.
It's moving into the carbonyl. So these electrons aren't going to be able to move into the carbonyl as much if these over there are doing the same thing. Because of that, esters are not as acidic as ketones. Now, aldehydes also apply here. The problem is aldehydes tend to be reactive in an aldol reaction. So it's kind of hard to make an anion of an aldehyde, although theoretically it's the same. So most of these examples we'll see ketones until we get to the aldehydes. Ester is less acidic. Why is the nitrile less acidic? I mean, if we consider a cyano group, if we draw it out, we can do resonance, yeah? But when we do resonance, where do we put the anion at? Put it on nitrogen, which is not as good as putting it on oxygen. Not as stabilizing, thus it's not as acidic. But we'll still be able to do the reaction. The acidity of these H's is on par with like the acidity of a terminal alkyne. Actually a little bit more acidic. That was another place we saw a CH having some acidity that we could use and do chemistry with. Remember the terminal alkynes, right? Acetylide anions. Okay, just for comparison, you know, look at this. This is a carbonyl and the alpha atom has an H. And the adjacent atom has an H. The adjacent atom has an H. But this is PKF5. Well, obviously that's a carboxylic acid there. But make comparison. This is a CH, that's an OH. Much more acidic. What about an NH? Alpha NH, which is an amide. Well, that's also more acidic. Because there you're putting anion on nitrogen and oxygen. Okay? Now we didn't talk about the acidity of amides much. But then you get to these compounds here, CH. So you see your trend here, anion on carbon, with oxygen being consistent with them all. Okay, let's look at tautomers. I think I'll turn the light back on. So let's review tautomers. Where did we see tautomers at before? Organic 1 with hydration of alkynes. Hydrating alkyne to give an enol, and the enol undergoes tautomerization to give the
Keto.
Yeah, we did that back in organic 1. And we actually, I think my guys, we did a lab, right, where we hydrated an alkyne. Yeah? Okay. So we introduced enols back then and tautomerization. Let's review that. We also introduced Oreo, I believe, yeah? Can we do that? Oreo, on resonance off, or off resonance on. Okay, here's a ketone here. The aromatic ring doesn't mean anything. It could be saturated, it could be any R group. Ketone, we can show an enol, right? There's your enol. Enol form, enol, right? These are actually in equilibrium with any ketone, equilibrium. Although with most aldehydes or ketones, the keto form, this would be the enol form, the keto form is highly favored, like 99.9%. In some rare cases, the enol form is more favored or even actually the favored form. We'll see that below. So usually we draw the structure like this, but there's a wee little bit of this in any ketone, an enol form. Converting between the two is catalyzed by acid or base. Catalyzed meaning it speeds up the conversion. Okay. How can we show mechanism in going between these two? Do you want to use acid or base in the example mechanism?
Use acid. Acid.
Acid? Let's use acid. That's the first thing I heard. Proton. How can we show this here? What do you want to do first? Well, we got carbonyl, we got a proton. What do we do first? Permanent carbonyl. Your favorite acid, whatever that is, what does that give us? It gives us, boom, carbonyl methyl, right? Permanent carbonyl. By the way, we now have an H on the oxygen. Isn't that what we're trying to accomplish? H on oxygen? Yeah. Okay, what do you want to do next? Resonance. Resonance. We can move the electrons up. Oxygen's electron greedy. Move the electrons up. What would that give? Now it has 2 lone pairs and plus charge here. Is that a resonance structure? Yeah, all we did was move pi electrons. We also moved them towards the oxygen, which is like really wants them now. And what do you want to do next? We did Oreo, right? What does Oreo mean?
For acid, it's on, resonance off.
Did we do Oreo in organic 1?
Yeah.
What does it mean?
Yeah, we did.
On res off or
On.
off res on?
Resonance. By the way, what did we do in the first step here? We put a proton on. And what do we do here?
Resonance.
We really didn't do it because it's just there, but we did it on the board.
Conjugate base can take the protons from the
What do we want to do now?
take the hydrogen off.
We're going to take it off. On resonance off. What H do you want to take off?
The one from
The one that needs to be taken off. Which one needs to be taken off? There's two H's here.
On the
There's
carbon.
3 there. Which one needs to be taken off? That one. Well, what gave up? What was with the H plus? Maybe Cl minus? I mean, there's got to be a minus here. Well, Cl minus can take it off. These 2 electrons do what? Move in here. That looks like a fast step of an E1 elimination. And when they move in there, what do we get? There we reform HCl. HCl was the catalyst. And what did we do in this last step? We took the proton off. So we can remember this mechanism by Oreo, which stands for on, resonance, off. That's your tautomerization mechanism. If we did this with a base catalyst, what would we do first?
Off.
Off. Because base takes protons off. Which one would we take off? The one that needs to be taken off. Can we take that H off? Yes, refer to what we talked about up top. It has some acidity. Then you would do resonance and you put it back on. So there's the acid catalyzed enol form. What's the definition of a tautomer? A single hydrogen has been relocated and also at least 1 pi bond. Right? Because in going from here to here, what have we done? We've relocated 1 hydrogen. One of the hydrogens on the carbon is now on the oxygen. That's the only atom that has moved in going from here to here. And then we've also relocated 1 pi bond. The pi bond is now between the carbons. You could relocate more than 1 pi bond. You could relocate 10. It's 1 hydrogen and then relocating some pi bonds. That's going to be tautomers. It's a specific type of constitutional isomer. We can also call this the CH tautomer because here the hydrogen's on the carbon. Where this would be the OH tautomer because here the H is on the O. Just some terminology. More on tautomers. Which of the following are enol forms of the compounds shown in the box?
First two.
Should be pretty straightforward. I mean, it's the first 2. I mean, enol, these are actually the only 2 enols up here. This is an alkene with an OH, but usually when you see the term enol, the OH is on the ene. So these are really the only 2 enols, but are these enols of that?
It appears so.
They are. Because, I mean, you can relocate the H on this side or this side. Both of these H's have the acidity, alpha hydrogens, either way. Which one is the more thermodynamically stable enol? First one, what? More substituted. It's the alkene rules. It's more substituted alkene. How many enol tautomers are possible for this compound? Show them. How many additional CH tautomers? We may have to explain CH tautomers, but how many enol tautomers possible for the following compound? Think about that. We'll look at it a little bit later. Please show them. Anybody got an answer right yet?
I got one of them.
Three.
The answer is more than one. How many?
Yeah.
So would there be three?
Okay, examples of enol being favored. This ketone here. The enol of the ketone here is actually the favored form. Why? Why is this the favored form and not the keto form?
Oh, resin.
Why is this the favorite form of this?
Aromatic.
Because it's aromatic. With the double bond in there, with the extra double bond in there, the ring becomes aromatic. So this is the favorite form. That's phenol. That's how we usually show phenol. But phenol, if you just focus right there, is actually that's an enol. That's the keto form, right? So there's an example of where the enol is favored. That's kind of duh. But it's actually, that's an enol that's favored. This guy over here, a little more not so duh example. 1,3-diketones. If that's 1, that would be 3. 1,3 relationship. 1,3-diketones typically exist like this, where one is a carbonyl, the other is in the enol form. That's typically favored. You can see that by NMR, if you run NMR of that compound. These are not resonance structures, right? Please don't confuse these with resonance structures. It's in the equilibrium area. In resonance, you never move atoms. Here, one of these H's has been moved to the oxygen. The remaining H is now on an alkene, which is going to be a different signal in the NMR than alkane hydrogens. The NMR of that compound will show what looks like a mixture of two. And it will, you're like, well, it's not pure. Well, it's a mixture of two. Quick question. Can you ever purify these two and separate and have just this?
No. I know this time. Last time I hadn't taken it.
You cannot do that. What if you had 100% of this?
Wouldn't matter.
Tough luck.
It's going to turn into that.
It's going to turn in, 85% is going to turn into that. You cannot have this compound as a pure one structure. It's a mixture of these two structures. Okay? But why is this favored? Why is the enol here favored? Give me a reason. There's actually two good reasons. Somebody see a reason? Conjugation. Here you have two different pi systems. They're not conjugated. Here you have all that's conjugated through there. Pi bond, lone pair conjugated with pi bond. You have an extended conjugated system. Conjugation typically is good. Okay? With that structure. What's another reason?
Substitute alkene. Alkene is one substitute.
The alkene? Well, this really doesn't have an alkene here. So we're not comparing two different alkenes. We could have drawn, note that I did draw the alkene here. I mean, if I had drawn the alkene on the other side and showed you this enol, that one's not good because, well, first off, this one's more substituted. But a bigger reason is this one has full conjugation. Here, this is not conjugated with that because you got the sp3 carbon. So the double bond comes in here conjugated, and it is more substituted. What's another reason though? Nice hydrogen bond. Nice 6-membered ring, 1, 2, 3, 4, 5, 6. Hydrogen bond is not a full covalent bond. First off, 4 bonds is better, right? Usually make a structure stronger. More. Well, hydrogen bond is not a full bond, but it's some bonding. It's partial bonding. This interaction is a stabilizing thing. Stabilizing for what? For the structure. So that intramolecular hydrogen bond also leads to some stability. So there's a couple of reasons why that structure is actually favored. We said here. So usually there's got to be some specific reason why an enol is favored. Otherwise, the ketone is going to be favored in more simple structures. There's actually in one of the handouts, I think it's maybe the white one. Where are we at here? Yeah, it's on the white next to the picture of the girl there. There's a couple of drugs. Used to treat MS. If you look at them, both of them contain enols. See the enol in the structure? That's actually the enol of a 1,3-diketone. I mean, if this was a carbonyl, it's just like what we looked at. This H can actually hydrogen bond here, and then this has an enol. It's also a 1,3-dicarbonyl. It's the same thing. Both of these have 1,3-dicarbonyls, which with the partial enol being the favored structure. Okay, chemistry. Alpha substitution reactions. What we'll do is we can do substitution reactions at this alpha carbon, and one main type is to halogenate at the alpha carbon. And here we're brominating. We can use elemental halogen, bromine, and then we can use something like this. These are going to be like catalysts. Acetic acid. A lot of times acetic acid is used as your catalyst because it's also can serve as solvent. It's not a strong acid, but it can be acidic enough to help the reaction. We'll start with single halogenation under acidic conditions. Mechanism for this reaction. The enol is a key intermediate. Enol. This is in equilibrium with the enol. And we showed this mechanism on the previous page, right? How to get here. Now on a quiz or something, you can't just say enol. You need to show the mechanism for getting here. But the enol is what really is the reacting species. Because at this point, this is nothing more, the next step is just like organic 1. You got an alkene, and you got bromine. Alkene is going to react with the bromine. Remember what we did back then? Where are we going to leave cation, left or right? I don't know how you guys did in organic 1, but the way I did it, we actually showed cation and said NAF, not actually formed. Okay, some people may go directly to a bromonium ion. We're going to leave cation on left or right? On the left. These electrons attack bromine, off. I'll just draw that phenyl. We get what? The cation plus Br minus. What do we do in organic 1 here?
Back bonds.
Back bond. Back bond to make what?
Triangle.
Bromonium ion. Right. But we said this is not actually formed because when you brominate an alkene, there's no carbocation. That was probably under B, no carbocations. Right? Actually, here though, this cation might form. How are we going to get this? Instead of this back bonding, something else back bonds. What if we bring these down? What does that give? First off, this is a resonance structure because these are pi electrons. It gives that, right? And then how do we get final product? This takes the H, leaves this behind, we get final product. What do we produce? HBr, that's the fate of the other bromine.
So if we use HBr and then generate even more HBr, does that mean that we're just making more catalysts so it goes like faster and faster as it?
Yeah, that's down below. Yes, we'll talk about that. For example, what if you don't use any HBr at all? We'll talk about that. Let's look at this real quick. This is just an alkene. What if we go back to organic 1 and act like we don't know any of this other chemistry and just brominate the alkene? What will we get? You think maybe we'll get, well, bromine here and bromine here? We just added bromine across the pi bond?
Oh, we've done that.
How could we possibly get that? This adding here? Yeah. In organic 1, you might say this is a product. Theoretically, yeah, but this is not going to be stable. Because anytime you can make a pi bond and kick off a leaving group, that's what's driven. And this thing's going to want to be split into 2 molecules. And this arrow movement gives what? It gives this. These electrons are going to kick that bromine off. So this is the way the water flows. And that bromine just takes the H and you got these 2 molecules. This is what you get at the end. Why do we make cation here, not here? Well, it's more substituted, but it's resonance stabilized. We put cation where it's resonance stabilized. This is an alpha bromination. If you treat this compound with bromine and acid catalyst, importantly, the reactive species is what? Enol with the double bond, the alkene. That's how this carbon becomes reactive. It's part of the alkene. It really has no reactivity as just a CH3. You can do this same reaction with chlorine. Take cyclohexanone, you can alpha chlorinate it. This would be done under acidic conditions. Under acidic conditions, you can monohalogenate. When we get to basic conditions, you'll see that you cannot mono. You have to exhaustively halogenate. Now, you can actually do this reaction with no acid catalyst. If you just take this and treat it with chlorine, it will alpha chlorinate. Remember, this is in equilibrium with what?
With
the enol form. You do not have to have acid catalyst for this equilibrium to be there. The enol, okay? The acid does speed it, the conversion up. By the way, let's go back to something. We need to make the point on the previous. I'll just lower this back down to right here. This equilibrium here favors which structure, A or B? It favors A. It's like this. Keto form is favored. Does that matter? Is that going to keep this from? No. There's some of this. And when it reacts, that means this is diminished. When this is diminished, what happens to this equilibrium?
So it starts turning back.
It shifts this way. So even though at one point this is much less than this, it shifts this way, and as it keeps going, all this gets pulled, and it all goes. Now this reaction down here is actually, it starts slow and then it speeds up. This converts to enol. Okay, the enol reacts, right? Enol is what really is reacting. It's slow because this is slow to convert to enol. Why does it speed up as the reaction progresses?
Because it makes catalyst.
Well, what do we produce here?
HCl.
HCl. The HCl that it produces can come back and start catalyzing the conversion from this to this. So it's called autocatalytic. It speeds itself up. It starts out slow and then it gets faster and faster as you produce the HCl. So you don't actually need the acid catalyst. Although you typically use it because why not? Okay, I think we're on number 2 here, is that right? Let's move to basic conditions. Under basic conditions, we're going to do exhaustive halogenation. Okay, based with hydroxide. Take this compound here. Exhaustive meaning we replace each of the CHs with a halogen. There's 2 H's, so we have 2 halogens. We have hydroxide. This reaction begins with hydroxide taking here, and we get the alpha anion, which on the first page we said we could make because this H has some acidity, pK of about 20. Now I'm going to continue on to the enol, but then we're going to come back to this structure here. On the first page we showed the conversion from keto to enol with acidic conditions. Here I'm showing it with basic conditions. I'm going to show the enol. 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 Get here with basic conditions. What's our mechanism? How do we remember it? Oreo, which stands for, under basic conditions, it stands for what? Yeah, we take proton off. Now what do we do? Resonance. These electrons can move here. These can move up. Double bond is going to be easy mix. We can do it either way. Actually, the enol can be easy. Okay, we did resonance. Now what do we do? O. On. Off. Resonance on. So we need to put proton on. Where do we need to put proton on? Right here. What's going to supply the proton? Water, because we make this plus water. There's certainly no acid here. Water is your strongest acid. These electrons take that and this. That gives us the enol, right? Plus what? What did we form here? Our catalyst was reformed. Isn't it amazing how when you say it's a catalyst at the end, it's always, there it is, it reformed? That's the definition of a catalyst. It does something, but it's miraculously, it's there at the end. So we put proton on. So O, but it's off on in this case. All right? But we kind of need to back up because under basic conditions, the enol is really not your reactive species. The more reactive species is this guy, this anion. By the way, what's the name of this? This is an enol. This is the anion of the enol. I suspect some of you are confused. How is that the anion of the enol? I mean, I don't even see an ene. Well, then, do you believe this? Is that the anion of the enol? I mean, there's the enol. We just take it anion. That's the anion of the enol. Everybody agree? Anion of the enol? Well, then that's it. Because neither one of these are the real structure. The true structure is somewhere in between these. So if I call that, it's the same thing. This is just one thing here. It's the anion of the enol. That's it here too. What do we call the anion of the enol?
Enolate.
It's that enolate. You might want to call it an enolide because ide is usually the chloride. It's called enolate because the A ending is also for. It's called enolate. You call it enolate anion. It's the anion of the enol. Now you can say this: which resonance structure is the major one for the enolate? Top or bottom? Yeah, that's the major resonance structure. Why?
Because
It charges on the oxygen.
Charge on oxygen. That doesn't mean we can't call that the enolate also. I mean, that's another form of it. Well, you gotta be careful. It's not another form of it. It's another fake form. It's another representation of it. Okay, but under basic conditions, it's the most reactive because it's an anion. If we get the anion and we have chlorine, these electrons can just attack chlorine and these get kicked off. What does that give? Well, it just gives that. And that's a monochlorinated product. Plus Cl minus. Here's the kicker though. That's a monochlorinated product that we just chlorinated the enolate. Can't stop here. Why not? We still have an H here. The hydroxide will take this H and make this enolate. I'm showing this resonance structure. I can show the enolate, that's enolate too. Make that. And then we come in with another equivalent of chlorine. We just do this, and we get that. We make two chlorides. The sodium will sit with the chlorides. What do we also make here if you completely balance this reaction? We also make two waters, right? Because each time the hydroxide deprotonated, we made a water. Why can't you stop here? Under basic conditions. Here's the answer. Which is more acidic? A or B? Which is more acidic? Actually, this guy's more acidic. To judge acidity, we look at anion. Which is more stable? This anion or this anion? I just told you this one because I said that's more acidic. Why is this anion more stable than the original one? Yes. Because the chlorine withdraws, it makes the anion more stable. So here's what happens in the course of the reaction. The reaction goes 1%. And after 1%, you have 99 of this and 1 of this. The hydroxide says, it's easier for me to come over here and do this. And you're like, no, I want you to just only deprotonate this guy. Hydroxide won't listen to you. It goes over here and deprotonates this. and it puts 2 on before it even puts 1 on over here. The second reaction is much more faster, and you just can't, you can't get a good yield of this. You have to go exhausted. You have to just replace them all. Because the product is more reactive by the fact that it's more acidic. So exhaustive. Please give product of this, and then we'll look at the haloform reaction. Exhaustive. Exhaustive, you're going to replace all of the acidic H's with your halogen. Reactive intermediate under basic conditions is your enolate. We can show the enol, but actually the enolate is an anion. It's more reactive. Enol tautomerization. There's a couple there to do, like the number of tautomers. Please. Okay, guys. See some of you in lab this afternoon, yeah? Finishing up. And quiz on Friday. Have a good day, guys.